Back to our next speaker, I would like to present Lindsay Walker.
Hi, my name's Lindsay Walker. I am the product and strategy lead at Lilypad, lilypad.tech. Today what I'm going to be speaking about is putting your GPU to work. We're going to talk a little bit about the research that our project based our work off of, and I'm going to talk about the opportunities and challenges that I see in the landscape of what I call high-performance compute network. So Lilypad is a project that is working to make it easy for anybody to run their AI models or other type of compute jobs on a network of decentralized nodes. So the question I'm asking here, what do you do with your GPU in a post-proof-of-work world? Don't be like Voldemort. Harry's asking, what happened to him, Professor? And he said he didn't reach his ROI before the merge. But this is not a bad thing. It means that we have a lot of compute resources available out there. So what are the opportunities and what are the challenges for the vast network of high-performing compute infrastructure that's available across the globe? Not only in individual miners, but in data centers. What do we do with all those GPUs? Of course, the answer is decentralized compute networks. Our vision is to give users access to all the models that end users need with confidentiality and integrity. In the research that I've done, there's different ways that you can categorize types of compute networks. There are networks that do GPU rentals, so you rent it by the hour and you can configure and run what you want on there. There's also API endpoint networks. They provide the models for you. You make an API call and you get on-demand GPU compute. There are networks that bring on groups of trusted nodes, and this is honestly the majority of it right now. And there are some networks that are trying to do trustless compute. So instead of having an SLA or some kind of an agreement, they use game theory and cryptographic mechanisms to ensure that we can rely on this network. There are networks that do TEE or confidential computing to verify jobs, and there are networks that use other verification methods. And there are different projects that are targeting generalized compute, run anything you want on our network, versus specialized. They may go for a vertical like gaming or AI inference. Some advantages of decentralized systems. You can unlock a market of data centers that are sitting with 50% idle compute resources. So for any given data center, 50% of those GPUs, CPUs, whatever you may have, are not being used. Decentralized systems are dynamic. They can scale up and scale down. They're resilient and fault tolerant. If one fails, there's plenty across the globe to pick up. It means efficiency. Again, we can use those resources that we already have. You don't have to be like Voldemort. You're not wasting your compute. And blockchain brings payment rails and transparency to these systems to make it possible. So let's talk about high-performance compute. Traditionally, these clusters or networks were put together in one geolocation. It means they had really, really high networking speeds. That means that not every single compute task that we used to put on HPC clusters are great for decentralized systems because we have lower networking speed. It means we can't do instantaneous inference like a chatbot as well. There's also a lot of latency because it means we have to move the data to run, say, an AI job to the compute node that is running it. That doesn't mean there isn't a huge opportunity here. There are things that are really well suited to these decentralized systems. Anything that's batch processing. If you need to run the same inference jobs many times over a large set of data, say you have a genome and you want to use an AI model to analyze it. It's a large set of data. We're making the same call over and over. Great for a decentralized network. Any jobs that's massively parallelizable, it means we can split it up across the network. And these decentralized networks also sort of have this opportunity of putting customized, uncensored, or fine-tuned inference jobs that you can't find elsewhere, which is something that Lilypad is working really hard towards. We based a lot of our work on a paper called Modicum, Mechanisms for Outsourcing Computation via Decentralized Market. I'm going to talk about what this paper presented, and then some of the things that we're using, and then some of the limitations. So the summary of this paper, it outlines a decentralized system for outsourcing computation. It's a network of crypto-incentivized actors. It deters actors from misbehaving with mediators or validators, and enforceable fines. No consensus mechanisms needed for that. They're not super efficient. It doesn't require global trust, and there are decentralized roles in this system: job creator, solver, resource provider, directory, it's mostly just storage, mediator, which we call validator, and a module creator. Let's talk a little bit about what these roles are. Job creators are the end user. You will kick off a job. Usually that might be an AI inference job. We have validators. Validators check those jobs to make sure you actually ran OLLAMA 3. You didn't go to Google and try to find the answer to it instead. Solvers match the job creators who have jobs with the compute resource providers. Resource providers are the ones who have that high-performance compute, the GPUs, CPUs, what have you. And then module creators are a pretty unique thing to Lilypad. Module creators are the ones that containerize and put the types of jobs on the network. That means you can put a fine-tuned model on there, and that module creator can monetize it. Every time that job is run, they earn a little bit of the fees generated on the network. It's a game theoretical model. We don't need to have as much security as, say, a consensus mechanism. So we don't need to validate 100% all jobs done by all actors. Most of the time, we just need to economically disincentivize what we don't want. We want to make it easiest and most profitable to just perform the job as intended. This is difficult in a game theoretic model. There's a lot of collusion that goes on. So it's not as easy as it sounds. We've been doing a lot of work experimenting with this, seeing how it runs in real life in our testnet. One thing we make a lot of use of is statistics-based job matching. So our resource providers, they have statistics, we record them, they go on chain for a lot of transparency. Lilypad job creators get bids by resource providers by price and by requirements. If you're a job creator and you want to use a resource provider, you can look at the machine specs, how much VRAM, how much RAM, how much CPU is available from this resource provider, but also statistics about past performance. How successful are you? How long does it take you to run modules? This makes it possible for the best actors to get the best jobs, but it also makes it possible for those who maybe you don't need the fastest resource provider and you're happy to pay less money for that. It makes that possible as well. We also have statistics on our modules. So again, those are those containerized and packaged compute jobs that are put on the network by module creators. We collect information about the average teraflops for the module run and the time to run a job. Resource providers use this on-chain information to calculate how much they're going to bid for a job. We have module run information, so people who are running the jobs know, okay, what's the success rate? How often does this run right? What type of machine specs does it need to run on? Resource providers also can allow list and set prices per model, or not. So these are some of the game theoretic mechanisms that we enable to enable the best actors to rise to the top and earn the most rewards from our system. Now I want to talk about why now. Why are we doing and why are we creating decentralized compute networks? Why didn't we do this 5-10 years ago? Well, there's a lot of idle GPU. According to the United Nations University, in 2024, the global GPU market size was $634 billion. That's a lot. That is a lot of market cap. In data centers, more than half of the GPUs are sitting idle at any given time, on average. So now we have this really great mature blockchain technology. We can create more efficient open marketplaces with better prices. There's a huge demand for compute. We have the tools to do it. And we have the resources. They're sitting there doing nothing. We have the crypto and Web3 community. These are open communities that can keep up with the speed of AI innovation. I am floored every day when I hear about the new models and new agents being built, especially in the Web3 community. The Web3 community has a ton of technical talent, eager to build and accelerate the growth of the AI ecosystem. Our universal and programmable payment rails, that is, blockchains with smart contracts, are really good for things like AI agents. They don't have to, have a wallet. We can use smart contracts to enable them. Most importantly, in the last couple years, there's been huge advances in parallel processing and containerizations. The CUDA toolkit and ROCm, being able to run what you want on those, your ML jobs, your AI jobs, that's new. That's just emerged in the past 2 years. We have Docker-enabled orchestration, so it enables us to sandbox and coordinate jobs on these different nodes. And a project that we use called Bacalao enables these workloads on untrusted hardware to run across a wide network. There are some really big challenges, and that's why I'm excited for the number of projects that we have going on in this space, these DPIN networks for AI. 4 enormous things that we have to solve to make these possible, especially if we want to have truly trustless networks. Trusted networks actually are also a good opportunity as well. But we need to build a reliable, decentralized network of non-homogeneous compute nodes. That means we have all these data centers with idle GPUs, but they're not just NVIDIA. We have AMD, we have GPUs with ARM architectures. We need to make sure our network can run on all of these different types. Validating is hard. It is hard, and it's a cool problem. So if we are running a job, usually it's easy to check if you have a deterministic job. 2 + 2 should be 4. Yeah, I can check that. With jobs like AI, you put one input in and you get a different output out every time. That's what non-determinism means. It is really hard to check if you don't know what the output is supposed to be. Like I was talking about with our statistics a little bit, it's hard to build a hardened and enforceable game theoretical model so your actors are doing what they're supposed to do and getting incentivized for it. And then security is a big thing. You want to build a product, your data needs to be secure, and the modules, the compute jobs you're running on these nodes need to be secure. You don't want malware showing up on a bunch of compute nodes. So I'm going to dig into these a little bit. Building network nodes, this is really hard. In order to capture the entire GPU market, that's 634 billion, the software needs to work on different architectures and different devices and different drivers. It means we need to also, the way ours works, that game theoretic model, we need to collect information and validate from all that different hardware. That means different software for each one, different drivers. It's hard to configure, so we install our Lilypad software on each of those nodes. It means that we need to be able to configure it for each of those nodes. And then we have those modules, which are the packaged compute jobs that are sent out over the network, also must be written and configured for all nodes on the network. So this is one of the things that I'm really excited to tackle at Lilypad. We've started with certain NVIDIA architectures, but we're starting to look at different architectures. How can we make this work on everything and unlock all those idle GPUs? Validation's hard. There's different ways people go about it. I kind of look at it in 2 ways. You can do pessimistic validation. You have to check everything. You assume no one's doing what they're supposed to. You check every single job run, and it can take a lot of work. Some of the ways people do that are generally cryptographic proving mechanisms. We use ZK proofs, fully homomorphic encryption. That's when you encrypt the data going in, you act over the data encrypted, and you send the data back encrypted. Or confidential computing, where all of the computing happens in a secure enclave on your node. There's also optimistic, which is what people tend to do, just because it's less expensive computationally and energy and everything. You have to run less jobs. We assume that jobs are run correctly, but we have some sort of random challenging. We can use some probabilistic methods with this as well. You can do GPU profiling. When I run this job on this type of GPU, what does it look like? How much power is it using that when it cycles through? What are the T-flops doing? What is, how much heat is it giving off? And NVIDIA SMI gives some really great information for that, but it's a little bit harder on different drivers. Semantic validation. You check it. Does it make sense? This non-deterministic output from an AI model, does it make sense? I ask you, what is America's most popular cat? If you say Garfield, you're like, okay, that makes sense. If you give me Snoopy, semantically, I don't think that person ran the high parameter AI model I was asking for. So I've done a little research on that, and there's an interesting landscape, but it's not very big. The projects I've looked at, and this is something Lilypad is thinking about as well, have a narrow set of types of compute they can validate. Well, we want to run any job on any node. A lot of these projects only can validate like a set of 5 LLMs. I have a method for this, but it only works for these 5 types of LLMs. There's a really cool project that can check ML flows, but it's limited to specific hardware. Some projects are experimenting with ZK proofs, but these are really computationally intensive and expensive, so it might not be a good alternative. It might be if it's a big enough problem, though. The other problem, game theory. I've talked about this before. We want to prevent cheating. We want to prevent collusion. It should be impossible to game the network. Ensure if you're running a job on the network, you're getting what you're paying for. We don't want certain actors to unfairly win more jobs than others, so that's a big problem to solve, a fun problem to think about. We want to prevent collusion between actors. Some examples of what this might look like. I talked about our actors before. We have our job creators, our resource providers, and then we have validators. A validator could collude with a resource provider and unfairly just send it all the jobs. We have to make sure that that can't happen. Or the solver, the one that does, that was the solver collusion. Validating could be you validate a job that didn't actually run. Security is huge, right? Currently, a big complaint is most LLMs you use openly. You get those free credits for it. They're collecting and using your data. If you are a paying customer that wants to use AI in your enterprise use case, absolutely not even a question. You have to protect intellectual property and personal identifiable information. That means there's 3 types of data you have to protect. Data in transit, getting the data in and out of the models. Data in use, that compute has to have integrity. It has to be confidential if you're running it on a decentralized node, or you can use a trusted node. Data at rest, not as much of a problem. We, at Lilypad, we kind of just send the data and we say, we're not storing this is yours. It's yours to deal with, but we could also outsource it to a storage provider and say, hey, you guys solve this problem of storing it. We also need to make sure that models have integrity. If we're allowing these AI inference jobs to run on every computer, we also don't want it to be setting up a botnet on that computer or something else that's really bad. So we want to make sure models have integrity and/or make sure that we have a really strict barrier between the models that we're running and the systems that they're running on. A couple things I'm really excited about. I think breakthroughs and advances in both of these things means that we'll be able to rapidly advance trustless decentralized networks. Fully homomorphic encryption. Like I said before, the data goes in, it's encrypted, it's acted on encrypted, it's sent out encrypted. It never gets decrypted, and the node can never see what's going on. It's really complex and expensive to compute. I read somewhere, but this was an old paper, that it's like 5,000 times less efficient. It might be in the hundreds now, but regardless, it's a lot less efficient. And there's a lot of other little details. It actually means the ciphertext, the data going in and out, is a lot bigger than the original. TEEs, also kind of known as confidential computing. It's not a secure enclave. The decentralized node running it has no access to it. There's protected keys within this enclave. The problem with that is usually these secure enclaves only work over CPUs. There's not wide availability, e.g. a big decentralized network, of TEEs that are acting over a GPU. I believe there's 2 types, like the Blackwell architecture. I forget what the other one is. There's 2 architectures that actually enable TEEs over GPUs. However, I bet you in the next 5 years, some of this stuff is going to be solved. It's going to become a lot more efficient, and it'll mean really big things for trustless decentralized networks. So yeah, I think that right now we have a lot of trusted networks, which is great. It means we're offering other options over big, expensive cloud providers where you can save 60 to 70% on high-performance compute costs. What I'm excited about is when we can see trustless, secure DAI networks with advances in fully homomorphic encryption, trusted execution environments, and ZK proofs. I want to give special thanks to our amazing engineering team. These are the people solving these really hard problems, implementing this very complex theoretical paper, and thinking about all the implementation details that weren't covered. So big thanks to our engineering team at Lilypad. And I'm Lindsay Walker. I'm the product and strategy lead. If you want to learn more about Lilypad, go to lilypad.tech. Follow us on Twitter. I am on Twitter, and I'm also on Blue Sky. We also just released an API, so I encourage everybody to go test that out. Thank you very much.
Thank you so much, Lindsay. We actually have some time for questions if anybody would like to field some. There are a couple of comments on YouTube if you want me to tell you a little bit about it. So Andrew said, yes, we also need it to prevent single point of failures if a nation state or a vendor decides to censor or give unfair advantages to competitors.
Yeah, that's a great point. That's why decentralized networks are really, really great. You might be able to cut off access, but with a decentralized network, there is no single point of failure, right? There's tons of nodes out there that can still do the job for you.
Yeah, that's beautiful. And then Jay said we need to decentralize compute to ensure everyone can compete and build AI-based applications.
Yeah, and one thing that Lilypad does really well is we allow you to run any model. It's really easy to deploy any model, so it means if you it's super easy to put it on the Lilypad network and monetize it.
Okay, thank you so much for your presentation. We look forward to seeing more.
Thank you so much.